I was saying that advantage function is the difference between your state action value and your value function. If this difference is huge, your advantage is huge, you're promoting that, encouraging that action, and in general that policy, because it's an iterative procedure. And so from one policy, you go to the other policy. From policy pi, you go to policy pi tilde, and you see the effect of that. And this is called policy performance, and you can increase your policy performance, eta. And state visitation, you see, when you want to reach a goal, for example, from here, this is starting point, you want to reach this point. Throughout this, for example, in the language of Markov chain, I want to talk I really enjoy Markov chains because it's more abstract, so you can think very easier. And so we start from here till the destination. Let's say this point is the destination. You visit some states. For example, in green function, if you have watched my playlist for Markov chains, about 20 lectures on these green functions and why state visitation is important. So, for example, you come here, and then you come here, and then, for example, there is a edge here, you go here, you come back to the state that you have already visited, and then you come here. So after a while, for example, if you have the Monte Carlo Markov chain, after a while, you can count how many times you have visited this particular or any particular states. And so you can understand all the, let's say, bottlenecks or anything. You can understand your state space better. And so when you change your policy, if you go from old policy to new policy, your state visitation changes. For example, you have a controller, and then if you change the controller, the states that you reach, for example, you have a chaotic system, comes here, and then after a while, you see that some states you have visited more than the others. But if you changed your policy, then some other states are visited more. So you should think about it like this. And there is a local approximation to eta. It's like maximization. Here I will explain it. Okay, we just try to approximate and create it's just maximization, minorization maximization algorithm. So, for example, when you have a non-convex function, you try to... I've written lots of articles about successive approximation, for example, to see how can we approximate iteratively. You can approximate and then through some successive approximation you can find the global point, at least suboptimal points, using these approaches. So this approximation is a little bit like that, like those paradigms. So we have actual policy cost function, you try to approximate it, and after a while you understand. And here is the lower bound. This is the lower bound for eta. And this researcher, I know this researcher, and they derived the following lower bound. And using this new policy, which is the combination of pi prime and old policy, you can have a lower bound which is greater than the, just like elbow that, in variational inference, you just to maximize elbow. Here is we have another lower bound. We just need to maximize that one. So this is the motivation for all of these things, because if you have that lower bound, you just need to work on that. So it's a good estimation, at least lower estimation, and at each step. This is the algorithm. At each step, you are trying to maximize this term, this objective, among all policies. But you never forget the previous policy, because I will talk about this Kl divergence here. So what is the total variation? You can approximate total variation between two distributions by Kl divergence. And 26, 27. I was saying that, okay, they created this lower bound, and this alpha could be extended to general policies. But if you just use, so instead of alpha, we use a distance measure, which it can be extended to general policies. But an epsilon is that, so we have this total variation. But instead of total variation, I said that we can replace it with this Kl divergence, and this is like minorization maximization algorithm that I was trying to say. It's really good to approximate this like this, and the reason is that we have a challenge here, because the Kl divergence is because the maximum is really hard it is non-smooth, and we don't like non-smooth things. It's challenging, difficult to optimize. So this is the reason that instead of maximum of Kl divergence, we use some average. So we use this average, and then things becomes easy. So we replace it by this average instead of maximum. And then we try to do some simplification, such as this one. Instead of this term, which is summation over rho, we use this term. Also, instead of advantage, we don't miss a lot of things, because it's already the same. It's just minus something, some offset. So Q is the major value. And another approximation is that, of course, we are using the techniques of importance sampling here. And I recall importance sampling in this slide, that if you want to find the expectation of f of x, because qx cancels with this one, so you can think about it like f of x like this, with this new probability. So this is the trick that we use in this importance sampling in order to justify this term. And this is the advantage function that I said. Advantage function, replace it just q, because advantage is already q minus that v value function. Just omit the value function. And what remains is that, of course, evaluating a Kl divergence is easy, because you just write the trajectories, and as I said, because they are independent, you multiply all of these things. But the good thing is this one goes with this one, so you don't even need to know the transition probabilities, and this is the beautiful thing. And finally, there are two variations in these two, let's say, variants of this paradigm of trust region policy optimization. And we need these single pass, or so you could even use single pass or wind procedure. So from here, it's like a tree that goes, and it's a branching mechanism. And so the first step is collecting a set of state pair actions using these, and also their Q values. So this is just the first step to provide those state action pairs, and of course their Q values. And the measure of intelligence is the ability to change. Words can be meaningless if they are used in such a way that no sharp conclusions can be drawn. When I first read this sentence, I wrote an article about my new word-to-vector embedding, because I used the concept, and it is accepted in America, but I don't have time to go there. So anything that you hear could have is telling you something in natural language processing. You should have a conclusion for anything. And for all of word-to-vec paradigms, we don't use this important sentence. And I have another idea as well. I should write another article about using reinforcement learning for natural language processing. And I encourage everybody to use reinforcement learning for word-to-vec, also for language translation. Also, in all parts of NLP, you can use reinforcement learning. And unfortunately, there are so many few articles about it. Maybe because traditionally people just use reinforcement learning for simple games like Atari, or simple projects like self-driving cars, or maybe robotics for picking some objects and those things. But reinforcement learning could be used for natural language processing a lot. Also for vision. Also for having better traditional supervised learning or unsupervised learning. And it's really nice. So I think that reinforcement learning plays an important role in unifying all concepts in supervised learning, unsupervised learning, NLP, computer vision, bioinformatics. All of them could be, especially dialogue generation. Think about it. When your robot is thinking, trying to generate a sentence, it thinks about, it has some, let's say, pivot points. Okay, I will explain it in some other lecture, because this lecture is just about theoretical things of reinforcement learning.